My name is Eric Knowles, and I'm an incoming senior at North Carolina State University in the Department of Materials Science and Engineering. This research concerns modeling proton transfer through barium titanate. Now, barium titanate is a very important dielectric and ferroelectric material used in capacitors, RAM, and certain kinds of resistors. Of particular interest is that of multi-layer ceramic capacitors, where thin electrodes are sandwiched between thin layers of a dielectric such as barium titanate. As these ceramics are engineered to become more powerful, these dielectric layers need to become thinner and thinner. In the case of barium titanate, when the layers become too thin, proton transfer dominates the process and may significantly impact the performance of the capacitor. The purpose of this research is to model the proton transfer process through thin layers of barium titanate. This utilizes diffusion with surface limitations, electrostatic drift diffusion, and electrode contact interactions. The primary platform of this model is Phoenix, which is an open source Python program which runs the finite element method, a useful tool for solving partial differential equations numerically. Additionally, I used Solus to gain insight into how wide bandgap, high dielectric materials interact with electrodes and with the drift diffusion equations. First, I modeled oxygen diffusion into barium titanate. Now, this process had been researched before, so I could compare values with those found in research and with an analytical solution. My first model utilized diffusion with a constant diffusion coefficient and a surface exchange coefficient. The results can be seen in Figure 1, where they are compared with the literature in Figure 2. After this, I attempted to look at Solus to see what useful information it could provide in how drift diffusion plays a role in charge carriers such as protons. One can see from the Schottky diode modeled that the depletion region is extremely wide, which can have a very large effect on conduction of charge carriers such as protons. Unfortunately, as I tried to add this drift diffusion process to the model, it became much more difficult than anticipated, and I was unable to do this successfully. As I ran out of time, I was also unable to model the electrode interactions between the dielectric layers. In the future, I would definitely like to finish adding the drift diffusion process, as it proved to be a very significant component to this model. The electrode contacts would also be important, but not quite as important as the drift diffusion process. As I was looking through the research on all the different types of proton conducting oxides, I found a significant lack in any model that was comprehensive enough to describe this entire process. And so the significance of this research definitely presented itself to me. Thank you.